So here we have a non-homogeneous equation that's going to lead us down an interesting path. So just to see what's happening there, let's just get right into it. So remember that the general solution is going to be y equals yh plus yp. So we always need to know the homogeneous solution first. So that, of course, comes from our characteristic. Whoops, getting ahead of myself here. We set the left-hand side equal to 0. We know by now that that equation leads to that characteristic equation. It looks like we have lambda plus 3 quantity squared equals 0, which means lambda equals negative 3 repeated. So that means that our homogeneous solution is this. Okay, nothing new. But now we have something interesting happening here. So looking at the right-hand side, it's a TE to the negative 3t. Now, in order to explore what the particular should be, instead of us guessing, because we don't want to guess wrong, do all that work, and then be left out in the dust. So I want to look at this as I know that this corresponds to lambda equals negative 3 with a multiplicity of 2. Which means I can use the annihilator method, which says I can apply an operator to both sides of the equation to convert it to a homogeneous equation. So since that's lambda equals negative 3 with a multiplicity of 2, I know that the d plus 3 squared operator applied to te to the negative 3t is equal to 0. Okay, so here's the picture. I'm going to first write the left-hand side in operator notation, which you might remember is d squared plus 6d plus 9 applied to y equals te to the negative 3t. All right, so I'm going to rewrite that as d plus 3 squared y equals te to the negative 3t. So I haven't applied anything yet. I'm just setting up the stage here. So I'm gonna apply another d plus 3 squared to both sides, because that's what's going to wipe out the right-hand side and make it 0. Now something interesting happens here. On the left-hand side, I now have d plus 3 to the 4th y equals. Now, you can go through and apply the operator to te to the negative 3t. You will get 0. So I'm just saving you the work. Okay, now, this is a strictly homogeneous equation, so I know that this is a complete solution. I know that it's going to be c1e to the negative 3t plus c2te to the negative 3t. And how do we keep going for higher multiplicities? We just keep multiplying by powers of t. The background theory tells us so. Okay. Now, what we do at this point is compare. We already know that this is the homogeneous solution, which means that this must be my particular solution. So I'm not going to go through it in this entire video, but you're going to say yp is, and you can use any constant you want. You don't have to use C3 and C4. You can use A and B if you want to, or whatever floats your boat. But there it is. So basically, here's the idea of what's going on. So without having to use annihilators, if you want to go right to undetermined coefficients and just do the guesswork for the particular solution, if you come back up here to the original differential equation, looking at this right here. So after looking at the characteristic equation, you get lambda equals negative 3 with a multiplicity of 2 on the left, and on the right, you know that that function corresponds to lambda equals negative 3 multiplicity 2. So combining them together, you need to account for a multiplicity of 4, which means whatever got soaked up in the homogeneous, the rest is the particular, which is why there's 2 terms. Now, are we guaranteed that both C3 and C4 are non-zero? No, but you know that at least one of them isn't going to be. In fact, if I'm thinking correctly, this one will hang around, this one will be 0. So if you're watching this on YouTube, leave me a note in the comments to tell me what happened. But I'll leave that to you, because the most important part was being able to figure out what the particular solution had to be. So there you have it. I hope that helps. Thanks for watching.